All right, folks, we are back at it again for 6-2 section of chapter 6, where we deal with linear and angular velocity. Many of you might have seen some of these concepts if you've already taken physics or are taking physics, but we're going to look at the mathematical basis of it. We're going to kind of stay on the simpler edge of the physics of it. So let's move over right away and get to the notebook. When we talk about linear and angular velocity, that's the title of the chapter, but it really should be angular and linear velocity, because you really need to understand angular velocity before you can understand linear velocity. So angular velocity, in order to understand that, we need to even go to a more basic idea, and that is angular displacement. All right, when we start talking about angular displacement, what we're talking about is if we have something that is circular, I'm going to use my handy dandy tool here to make a circle. If we have a circular object and we have a point on the edge of that object, as this circle, or as it rotates around this circle, or you can say as the circle moves, either way, as it moves around the circle, how far it moves. So say this point that's on the edge of the circle rotates around the edge of the circle this far. All right, it stops here. So it rotates from here around to here. Well, from the center, the number of degrees or radians that it's moved through, and we're going to use radians more than anything here, that theta that it's moved through is its angular displacement. And is, as a kind of a formal definition, it would be a circular object that rotates about its center. The object at its edge moves through an angle relative to the object's starting position. So again, relative to its starting position, as this rotates about the radius, as the circle moves and rotates this point around the radius, that displacement in an angle is its angular displacement. So what does that look like? Well, if we wanted angular displacement, they could tell you something like that, and we're going to work in radians here again, guys. Everything we do here is in radians, because you're going to find radians, again, have that relationship with lengths and distances. So in radians, find the angular displacement, and I'm going to shorten that, angular displacement of 3.5 revolutions. Now, what I mean by that is if we had a point on the edge of a circle and it rotated that circle, that circular object, rotated 3.5 revolutions, how many radians would it move through? All right, what number of radians? Well, think about what that means. If we have, again, that object, and I'll just use the same circle to shortcut it. If I have an object starting here and it goes around this circle 3.5 times, how many radians has it passed through? All right, an easy way to think about that. If it rotates one full rotation, how many radians has it passed through? Well, how many radians are in an entire circle? 2 pi. So it's rotated 2 pi radians in one complete circle, and it did 3.5 rotations or revolutions. So we could just multiply 3.5 times 2 pi, and you would have 7 pi radians. Now, if they ask you to do this to the nearest tenth, then you would multiply 3.5 times 2 pi and take that 7 pi and multiply it, and you would get, let's see, what is 7 times pi? 21.991, so we'd say 22 radians. Now, it's not unusual. If you don't see anything, like if you see 22 and there's not a degree symbol, we assume it's radians. If theta is 22 radians, then, or 22, that's considered radians, all right? So you could technically see any angle given to you that doesn't have a degree sign, you've got to assume it's radians, all right? And again, we'll talk about that more as we go through. But so angular displacement is that basic concept that as we rotate around, however many revolutions we create, that times 2 pi would give us the number of radians of angular displacement, all right? Or angular displacement in radians, if you want to say it that way. So If we understand this concept of angular displacement, which is an if, but I can always clarify it for you tomorrow if it's not perfectly clear. Let's talk about angular velocity now. Like I said, we have to start here, even though the title of the chapter lists them in reverse. Angular velocity is something we are going to deal with quite a bit. When we talk about angular velocity now, we're talking about the angular displacement in relation to a unit of time. So we're used to this. We're used to velocity being something like feet per second, meters per second, things of that sort. We're always talking about a length in relation to a time, right? So meters per second, or miles per hour. All of those are velocities. They're not angular velocities. So angularity velocity, I just realized what I wrote there. I just want angular velocity. I kind of combined angular and velocity into one word, angulosity. Sorry about that. Angular velocity. All right, so angular velocity is what we're talking about is again, instead of talking about how fast something's going in a line, like miles per hour for a car, we're talking about with a circle, again, a point on its edge. If we have some point on the edge of the circle, as the circle rotates, how fast is this thing moving around the circle, whichever direction, it doesn't matter. How fast is it moving in an angular direction? Well, in order to talk about this, we need to talk about something else. All right. We have to, again, start talking about angular displacement with relation to time. So what we're saying is instead of linear displacement, like miles per hour would be a linear displacement. If I say 55 miles per hour, I'm saying that that car moved 55 miles in an hour. It was displaced 55 miles in a line over an hour, right? It's in an angular or in linear motion. Now we're talking angular motion. So we need angular displacement in relation to time. And the symbol we use for angular velocity is omega. All right, omega is kind of like a stylized W, a lowercase w. Omega is our angular displacement over time. So we talk about this as theta over t, that angular displacement over time. All right, so this is in radians. And this is whatever time unit we are dealing with at that problem. So what would a problem look like for this? Well, a problem for this would be something like this, where we'd say, determine the angular velocity let's see, if 8.2 revolutions are completed in 3 seconds. Now, let's make it 3 minutes. I want to demonstrate something else. Let's say 3 minutes. It's moving slow. All right, well, not really slow, but slower. In 3 minutes. All right, we want to find it, and let's say round to the nearest tenth. All right, so you're going to see these type of problems. So let me get this out of my way. All right, so what are we going to do with this? Well, let's look at what we need. We need rho. They asked you for angular velocity. So if they're asking for angular velocity, which they did here, we've got to work towards that. So we're going to find rho. Rho is the angular displacement. What is the angular displacement? They told us 8.2 revolutions, right? That's all. That's how many we've gone. Not in a matter of time, just how many revolutions. But we need that as radians, right? So let's figure this out. Let's see, we've got 8.2 revolutions, and we know each revolution is worth 2 pi radians. So that's our theta, right? That's in radians. That's converting the revolutions to radians. And it's completed in 3 minutes. That's our unit of time. All right. So what we end up with is going to be radians per minute, right? Because we have revolutions, which are just how many times in a circle, times radians. Radians are the unit of length, and over minutes. So we're going to get this in radians per minute. So 8.2 times 2 pi, let's figure out what that is. If we do that times 8.2, we get 51.5, I'm going to say on top. I'll go out a little bit, 522, 51.522 radians. And that's over 3 minutes. So we're not yet into radians. We want a single unit of time on the bottom. We've got 3 minutes. So I'm going to divide by 3, and I'm going to get an answer of 17.7. I'm sorry, 17.17. I'll read my calculator correctly here. 17.174. And that's in per. Now, for the nearest tenth, so I'll say 17.2 radians per minute. Now, they could ask you in a problem like this, what if I wanted it in radians per second? I want my rho, or my omega, I'm sorry, in radians per second. I want this angular velocity per second. Well, if it's 17.2, this is where we go back to our idea of dimensional analysis. It's 17.2 radians for 1 minute. I need to change this into minutes. I need to change minutes into seconds. I already know how many radians, right? I need to change minutes into seconds as my dimensional analysis. If you remember, I just set up a little multiplication box here that helps us. I need to change minutes, and I know in 1 minute, there are 60 seconds, right? So the minutes cancel here, and if I multiply across, I would get 17.2 radians every 60 seconds. And that would come out to 0.286 repeating as radians per second. So if we wanted to go to the nearest, we'd say 0.3 radians per second. So again, angular velocity is how fast is it moving around that circle? How fast is it moving on the angular path that it's going? Unlike when we talk about miles per hour and such as a linear distance, this is going to be on an angular distance, and that's why we do radians. All right, it's going to be given as a measure in radians per unit of time, a single unit of time. All right, the last step we have to take is we go from angular velocity to linear velocity. I'll stay in blue, I guess. All right, when we move to linear velocity, if you notice, everything is kind of built on one another. It's the same idea. So what we're going to do is, again, I'm going to get my circle. Now, with that circle, what I'm going to say is, all right, what if that circle is actually a wheel on, oh, let's do a bike. And I'm going to draw a really bad bike. Yeah, this doesn't make any sense. This is kind of what a bike looks like, right? And we'd have another circle out here, which would be centered there. All right, so we'd have that, and whoops, I want that. We'd have handlebars and a seat. All right, so we've got a bike. Now, on this, if this bike, these wheels are rotating. These wheels have a certain angular velocity. They have an omega value. A point on the edge of this wheel would rotate so many radians per minute, second, whatever unit of time you chose, right? Now, what happens as this wheel is rotating, this wheel would also be rotating at, if it's the same size, at the same angular velocity, right? It's going to be rotating. What happens to the bike? That angular velocity of these wheels is translated into, because they're attached to the ground. Now, these could be pulleys, right? You could also have where you have pulleys with a, let's see if I can do this. If we have some pulleys connected, or yeah, we'll do that. No, it won't do that one. All right, let's do this. So we've got pulleys with a belt connecting them going around this. These again would be rotating at a certain angular velocity. The belt would be moving in a linear velocity. Whatever's on that belt would be moving in a linear fashion. So there's a lot of ways of taking angular velocity, and just think to yourself, all the ways you see wheels, gears, things of that sort that are rotating that create a linear path for whatever they're rotating with. So like this. So what we've done is take this angular velocity and translate it into a linear velocity. Now, how does that happen? How do we do that? How do we do it in terms of the math? Well, linear velocity we call V, just capital V. And V is equal to our angular velocity times the radius. Now, I should have written it that way. I always think of it this, well, no, I'm going to write it the way I said it. Angular velocity times the radius. You'll also see written this way. I always learned it this way. I think your book uses this order. It doesn't matter. You're still just multiplying the radius times the angular velocity. So what is that doing? Why are we looking at this radius value and translating it into a linear velocity? Well, think about how the radius relates to how far this thing goes. If we talk about the radius, isn't the radius going to be 2 pi, or I should say, isn't the circumference of this wheel 2 pi r? So every rotation, it would move the circumference of the wheel, wouldn't it, in terms of distance? Again, circumference equals 2 pi r. And in omega, we already have the 2 pi, don't we, because it's part of angular displacement? So all we have to do is multiply the r, and we find out how that circumference, how fast it's traveling along that circumference. So velocity just multiplies the radius of whatever is rotating times the omega, the angular velocity, how fast it's going around in a circle in radians per unit of time. And that translates it into a distance per unit of time. All right. So what does a problem like that look like? Well, let's look at a problem. If we say determine the linear velocity of a point rotating at an angular velocity of 13 pi radians per second. At a distance of 7 centimeters from the center of the rotating object. Round to the nearest tenth. All right, so if we look at this, the way you have to analyze these problems, there's a lot of words in these problems in this section. So you've got to be able to kind of look at what is it asking me, all right, and be able to translate that into a problem. So determine the linear velocity. First, to find out what they are asking you for as an end result. We want a linear velocity. So right away, what I do when I determine the linear velocity. So linear velocity is this. All right, I'll use your book version. R times omega, right? Of a point rotating at an angular velocity. They just gave me angular velocity of 13 pi radians. This is our omega, right? That's this thing, 13 pi radians per second. So they just told me, and so I'm going to write this to the side. They told me omega is 13 pi radians per second. All right, at a distance of 7 centimeters from the center of the rotating object. What do they told us there? Distance of 7 centimeters, that's our R. So R equals 7 centimeters. So let's look at this. Now we can say velocity is equal to 7 centimeters times 13 pi radians per 1 second. All right, well, we want to think of this way, 7 centimeters over 1 and 13 pi radians over 1 second. So when we multiply this out, what we end up with is 7 times 13 pi. All right, 7 times 13 times pi is 285.88. 285.88, so we'll call it 285.9, and that looks horrible. My writing there was not good. So 285.9. And what are my units here? Centimeters times radians equals centimeters, and it's per second. So this is in centimeters per second. And we've got our linear velocity. Velocity is 285.9 centimeters per second. All right, let's do another one of those. Let's say, let's use our bike idea. If we have a bicycle, and for this bike, we have a wheel of radius, let's say 24 inches. And it's rotating at a speed, and I'll say an angular velocity of, let's call it 10 pi radians per minute. Let's do a little bit higher. Let's make it 20 pi radians per minute. All right, so rotating an angular velocity to rotate at of 20 pi radians per minute. Find the linear velocity of the bike. So let's do this. What did they give us? Well, they gave us the radius. So we have R, right? This is our R. Whoa, I did it again. Every time I hit that button. So this is our radius. And this is our omega, right? So velocity, and they want us to find the linear velocity. So velocity is R omega. So our R value is 24 inches times our omega of 20 pi radians per minute. So what do we end up with here? Well, 24 times 20 pi is 1507.96. So let's say 1508. That's 1508. And what are our units on this? Inches and minutes. So that's inches per minute. Now, does that mean anything to you? Do you know how fast 1508 inches per minute is? Probably not. So let's make this useful. And sometimes they'll do this. They'll say something like give, or they'll say translate the linear velocity into miles per hour. So if we want to change this to miles per hour, what do we have to do? Well, let's look at what we have. We're going to just do a dimensional analysis now. And you could have done this if they'd asked this right from the get-go. You could have probably done it right off the bat, changing like that 24 inches into 2 feet or that kind of thing. But let's just do this the way we have it with what we've got. All right, we got 1 minute. So we need to get minutes to hours. That's one's pretty straightforward, right? If I want to go minutes to hours, I know that there are 60 minutes And you always want the units to cancel. So you want one on top. If I'm getting rid of minutes, the minutes have to be on top. And our conversion factor is 60 minutes to 1 hour. So minutes cancel here. So what's left is going to be hours. So we got our hours. Now we need inches into miles. So inches. Well, I don't know how many inches are in a mile, but I know how many inches are in a foot. So inches are on the top, so I'm going to put inches on the bottom. There are 12 inches in 1 foot. That's my conversion factor, right? 1 foot is equal to 12 inches. The inches will cancel here, and I now have feet per hour. Still not where I want. So I need to get feet and miles, right? I know how many feet. This is a number you're going to want to put into memory. 5,280 feet per mile. All right, that's something you got to know, guys. All right. So let's do that. How are we going to use this? There's 5,280 feet. That's going to go on the bottom. And 1 mile is going to go on top. And the feet will cancel. So when we go across here, the only thing that's going to be left when we multiply across is miles. So this is going to equal 1,508 times 60. 1,508 times 60. And that's 90,480. And that's in miles. And we're going to be multiplying across here. 1 times 1 times 12 times 5,280. 12 times 5,280 is 63,360. 63,360, and that's going to be in hours. So now we don't leave it that way. We divide these. 90,480 divided by 63,360 is 1.428. So 1.43 miles per hour. Not very fast. That's slower than walking. That's probably someone walking their bike, not riding it, right? So that's our mile per hour conversion. All right. And that's what they're going to ask you to do. They're going to give you a variety of problems. This is going to come up in all different ways. But what it comes down to are these basic ideas. You need to know what angular displacement means. You need to know that that is the number of radians that are done. And it usually given to you as revolutions that you have to translate into radians, right? That's the distance or the number of radians a point on the edge of a rotating object moves through. Then you take angular displacement and you combine it with a unit of time and you get angular velocity, right? And there we're going to be talking about things like radians per second or radians per minute. And it's always going to be that kind of combination. Finally, if we take angular velocity and we attach something to it that moves in a linear fashion, then we can get linear velocity from a rotational or angular velocity. And that linear velocity is going to be our common units that we're used to: kilometers per hour, meters per second, miles per hour, that kind of thing. All right. So again, we're going to use these in a variety of ways and try every problem. This is one of those sections that I every year I have people just kind of quit on when we go through them the first time. Make sure you work through it. Do your best with every problem. Bring all your questions to class tomorrow, and we'll handle them. All right. Have a wonderful day, and I will see you then.